All right, Algebra 2. This is our video on complex numbers, also known as imaginary numbers. And actually, there is a pretty distinct difference between what we call complex numbers and what we call imaginary numbers, and I'm actually going to cover that. So without further ado, let's get started. First of all, the imaginary unit. Excuse me, the imaginary unit is that little I. So numbers such as I root 5, negative 5i, and 2i are called pure imaginary numbers. Little I is the imaginary unit. Using the imaginary unit, you can define square roots of negative numbers. So the basic definition of that imaginary unit, however, let's do that first, is that the square root of negative 1 is equal to little I. And you can find that little I on your graphing calculator. You can put your graphing calculator into A plus BI mode out of the real number mode, and it will actually do some of the computation for you with the imaginary numbers and complex numbers, so that's nice. But for any positive real number b, the square root of the opposite of b squared, or of negative b squared, is the same thing as taking it apart and making it the square root of b squared times the square root of negative 1. Square root of negative 1 is I, and square root of b squared is b. So bi would be the square root of negative b squared. Okay, and again, that I is the imaginary unit. Now, quickly before we go on from there, what's the point? Why? Why do we need these? Without imaginary numbers, we can't solve equations like x squared equals negative 9. And there are some real-world applications where we will need to be able to solve equations like that. The difficulty with the imaginary unit and the complex numbers that kids have is that they can't visualize it the way that they can with real numbers. So if you can get around that part, these are not that complicated. You just have to follow some specific rules. Let's look at a few examples. Let's do the square root of negative 12. Well, first of all, 12 is not a perfect square, so I'm not going to be able to find just a straight up square root. But I do know that I first have to think about this as the square root of 12 times the square root of negative 1. The square root of negative 1 is I, and the square root of 12 can be simplified. 12 is 4 times 3, 4 being a perfect square, so 2 root 3 is the simplified version of the square root of 12, and then I. And you could put 2i root 3, which is probably the most common way that you'll see it, or 2 root 3i. Just make sure that your little radical roof here doesn't go over the I as well, because we're not saying square root of I, we're just saying I. So we simplified the radical to 2 root 3, and then we simplified square root of negative 1 to I, so 2i root 3. Next one, square root of negative 27x cubed. Well, if I have the square root of negative 27, I have the square root of 27 times negative 1, and then I have x cubed. Well, I can break down that x cubed into x squared times x. So the square root of negative 27, I can't do. I need to simplify that. I'm sorry, the square root of 27. I need to simplify that, as we know how to simplify radicals. I can do the square root of negative 1, and that's a dot, not a subtraction sign there. And then for the square root of x cubed, I'm actually going to break apart x cubed into x squared times x. So while we haven't really reviewed this quite yet this year, this is really the same thing as considering 27 9 times 3, saying I can take the square root of 9, that's 3 root 9 times I times. I can take the square root of x squared, that's x, and then I have a root x on the outside. So this is 3ix root 9x. All right. Negative 3i times 8i. You're going to start off by treating that I as if it's a variable. So you're going to treat this like it's negative 3x times 8x, which would be negative 24x squared, but we're going to write I squared. But I squared has a value. If I by itself is the square root of negative 1, then squaring both sides of that, I squared gives me negative 1. And these are 2's. They're just really messy 2's. There we go. So negative 24i squared, I'm going to cross out the I squared and make my negative 24 a positive 24. So negative 3i times 8i is indeed positive 24. All right, square root of 6 times the square root of negative 6 times the square root of negative 10. Let's separate it out first. The square root of 6 times the square root of negative 1 times the square root of 10 times the square root of negative 1. Square root of negative 1 is I. Square root of negative 1 is I. I can't simplify the square root of 6 or the square root of 10 by themselves, but if I put them together and make it square root of 60, that I can simplify. So let me get rid of these i's real quick. Let me put this back together and make it square root of 60 times I times I. 60 has a perfect square factor of 4 in it, so that's 2 root 15. So 2 root 15 I squared. I squared is a negative 1, so negative 2 square root 15. Excuse me. All right, last one. High powers of I. These are actually a lot easier than you think. Here's what I want you to do. I want you to think about how you could rewrite this as first an even exponent and then leftovers. So I to the 25th is I to the 24th times I. Good so far? Of course. Then we're going to rewrite I to the 24th as I squared raised to the 12th power. And we know that because 12 times 2 is 24, and that would give me that exponent on that I. So if I now have I squared to the 12th power, that's the same thing as saying negative 1 to the 12th power times I. And since 12 is an even number, that negative 1 to the 12th power is a positive 1. So it turns out that I to the 25th power is just equal to I. Okay, now, why did we need imaginary numbers? Well, here's two equations right here that show you why we need imaginary numbers. All right, so when we solve a quadratic equation like this, where there is no linear term, so there's no x by itself term, actually, I kind of liked that blue arrow better. Let's switch back to that. We can do it by just solving for x here. So we can actually solve this by actually going through and just saying, how about we, let's make that thicker. How about we subtract 9 from each side? Minus 9, minus 9. 4x squared equals negative 9, divide by 4, divide by 4. X squared equals negative 9 over 4, which I can square root. And what we know about taking the square root of both sides is that we actually have to put a plus or minus in front of our answer. And then it's plus or minus the square root of negative 9/4, which we know is going to actually have, is going to be an imaginary number, is going to have the imaginary unit in the answer. So the square root of 9 is 3, the square root of 4 is 2. So this is positive and negative, 3 over 2i. Okay, same idea here, except this time I can subtract 56 from each side and then divide by 2. But it's still going to be negative. So I'm going to have x squared equals negative, in this case, let's see, half of 50 is 25, half of 6 is 3, that's 28. Square root. So I have x equals, again, plus or minus, the square root of negative 28, which is 2i root 7. Plus or minus 2i root 7. So now we have solutions for equations that look like this. And here's where we get to the actual difference between the imaginary number and the complex number. So imaginary number is a single term with I, with the imaginary unit in it. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers, and I, gotta love that it auto-formatted for me, is the imaginary unit. So 5 plus 3i is an imaginary number that's in that format, a plus bi. And when we're simplifying expressions of this type, we are merely using our rules for variables. So let's add 8 minus 5i plus 2 plus I, and we're just going to add basically what we would consider the like terms. So let's think of the constants as like terms, and let's think of the imaginary units as like terms. So 8 plus 2 is 10, and minus 5i plus 1i is minus 4i. And it does stay that simple. It doesn't get a whole lot simpler than that. On this one, we just got to make sure we distribute our minus. So this is 4 minus 2, which is 2. And then 7i minus 3i, which is positive 4i. Okay, now these are a little bit different. We are going to use our good old friend FOIL for the multiplying. Remember, that means first, outer, inner, last. So first is the product of 4 and 3, which is 12. Outer is the product of 4 and minus 5i, which is minus 20i. Inner is the product of 2i and 3, which is plus 6i. And then last, the L is for last, is the product of 2i and minus 5i, which is minus 10i squared. Now I'm automatically going to cross out that I squared and switch the sign of that minus to a plus for that 10. And then I want you to treat this like there are like terms again. So 12 and 10 makes 22. So 12 and 10 makes 22. And then minus 20i plus 6i is going to make minus 14i. And that is going to be the correct answer to C. So we simplify it down by multiplying. We have to use FOIL because of because these are binomials, these complex numbers. And we're going to do the same thing with the last one. So let's do that. And why don't you try it without me? Notice that these two actually have a relationship. It's the same thing, 1 plus 1 minus. Just something to point out there. Why don't you pause it and try it? All right, first, outer, inner, last. Let's do first, 16. Outer, minus 8i. Inner, plus 8i. Oh, that's interesting. And then last, minus 2i squared. So again, go through, look at your simplifying. So I squared is negative 1, so that's now a plus 2. And minus 8i plus 8i cancels out. So this becomes 16 plus 2, which is 18. So just something to understand here, these two are conjugates of one another. And when you multiply two imaginary or complex conjugates together, you get a real number. So complex number times its conjugate equals a real number. I should say real, but it's terribly messy. Let's try that one more time and we'll be done. And that is your crash course through imaginary and complex numbers. See you guys in class.